Hi everyone, and welcome to Unit 4, Lesson 2. So we're going to continue talking about chemical bonding, and today we're going to focus on ionic bonding. You may recall from Lesson 1, we talked about the three different types of bonding: metallic bonding, ionic bonding, and covalent bonding. In Lesson 1, I just touched on ionic bonding by again identifying what is actually taking place in an ionic bond. Today, we're going to reiterate that and go further by explaining some of the properties that we observe with ionic bonding. So the first question that we want to answer is, what is an ionic bond? And we're going to differentiate ionic bond and ionic compound using the definitions found in the back of your text. So according to your textbook, an ionic bond is a force that attracts electrons from one atom to another, which transforms a neutral atom into an ion. In Lesson 1, we learned that differences in electronegativity govern whether or not we form a polar covalent, a nonpolar covalent, or an ionic bond. When we have really significant electronegativity differences, the atoms are not able to play nicely with one another. Instead, the more electronegative element steals an electron from the less electronegative element, forming a positive ion, a negative ion, and as a result, an ionic compound. Now, if you notice the second definition, an ionic compound is a compound composed of ions bound together, and I'm going to use this term frequently, an electrostatic force of attraction, which is a fancy way of saying a bond between something that's positively charged and something that's negatively charged. You can see in looking at the illustration on the lower right that we have a sodium ion and a chloride ion bound together. Sodium, again, is called the cation because it's positive. Chloride is called the negative ion or anion because it's negative. I found a second picture of sodium and chlorine bonding together, and I thought this picture did a better job of illustrating the changes that occur when an ionic bond forms. Mainly, sodium loses its outermost energy level, forming a much smaller sodium ion. Now, this picture is not very good at illustrating this, but chloride gets slightly larger when it gains an electron because the proton to electron ratio decreases. Regardless, the result is an electrostatic force of attraction between a positively charged sodium cation and a negatively charged chloride anion. So what we're going to do now is take a look at some of the properties that we associate with ionic bonding. The first thing that we're going to notice is that ionic bonds tend to be brittle. So if you imagine an old container of sodium chloride or table salt, you might break open the box that it's contained in and find just one huge brick of sodium chloride. Well, unlike metals, if you tried to bend that brick of sodium chloride, you would quickly find out that sodium chloride is a brittle compound, meaning it breaks apart rather easily. And this occurs because when you bend sodium chloride, like charges will align with one another. The result is positive and positive lining up, negative and negative lining up, and a repulsion of these positive and negative ions, fracturing that ionic compound into multiple pieces. Another property of ionic bonding is electrical conductivity. So you'll notice from the diagram below that ionic compounds conduct electricity in one of two phases. The first is molten, which is a fancy way of saying melted. This is actually more difficult to achieve than you might think. Most ionic compounds have really strong bonds and therefore very high melting points. So even though allowing for electrical conductivity in the molten phase is possible, it's not very likely in most circumstances. More easily attainable is getting ionic compounds to conduct electricity in the aqueous phase. This is done by taking the ionic compound and adding it to water. The bonding properties between ionic compounds and water allow for the ionic compound to dissolve or break apart, forming positive and negative particles. This allows for electrical conductivity in an environment which is much more attainable in terms of temperature. One of the other points that I want to make is that during ionic bond formation, energy is released. And this occurs because the sodium ion forms a lower energy state by vacating that outermost energy level. and the chloride ion, or nonmetal, even if it's some other element, achieves a more stable 8-electron configuration as a result. So if we examine the energy behind the formation of sodium chloride, you'll see that 788 kilojoules, kJ, are released during the formation of a single compound, a single sodium ion and chloride ion pairing up. Now, this is actually taking place millions and millions and millions of times, and that 788 kilojoules is the result of that happening 1 mole of times. You might remember the term mole from Unit 1. That energy that is released is known as lattice energy. And it turns out that the amount of energy released during ionic bond formation is actually equal to the amount of energy that you would need to put in order to break that ionic bond. So this energy, known as lattice energy, not only represents the energy released during bond formation, it represents the amount of energy needed to break apart or to separate those two ions from each other. If you notice, I've posted a table on the right side that shows the lattice energy of different compounds. Now, we're going to focus on a few of these in particular. So let's take a look at the equation for lattice energy, which is now showing up on the lower left. You'll notice that lattice energy takes into account a few factors. The first one is a constant. So this is a number that has the same value regardless of which compound you are talking about. The other part of the lattice energy equation are the charges. So those are represented in this equation by Q1 and Q2. So let's say we're talking about a group 1 element that would have a positive 1 charge, or a group 2 element having a positive 2 charge. The final piece in the lattice energy equation is looking at the distance between the ions, and that part is in the denominator. That's going to be important because it determines what factors influence an increase in energy or decrease in energy. So now, let's look at melting points, and we're going to study these in terms of some group 1 and group 2 compounds that form ionic bonds. So ionic compounds, as I mentioned earlier, have very high melting and boiling points. And again, that's because the electrostatic force of attraction in an ionic compound is extremely strong. Let's identify 2 examples. So in the first slide here that's talking about melting point, we're going to look at lithium fluoride and potassium bromide. Lithium and fluorine are both in the 2nd energy level, really small, so 2nd energy level on the periodic table. Potassium and bromine are both located in the 4th energy level, much larger, much further down on the periodic table. Notice that the lithium fluoride has a higher melting point than the potassium bromide. Now, I chose these examples on purpose. They all have positive 1 and negative 1 charges. So the melting point is, the difference in melting point is going to be based on size and not differences in charges. So you'll notice that the smaller sized LIF has a higher melting point than the larger sized KBr. Looking at the equation, if the charges are the same, Q1 and Q2, but the distance between the ions is greater, that means the denominator is getting bigger, the lattice energy, the amount of energy to pull it apart, is going to decrease. Thus, we observe that as lower melting points for bigger ionic compounds, smaller melting points for, or greater melting points for smaller ionic compounds. Let's take a look at a second example of how melting point is affected according to the lattice energy equation. This time, we're going to talk about sodium chloride and magnesium sulfide. All 4 of these elements are located in the 3rd period on the periodic table, meaning their sizes are relatively similar. However, sodium and chlorine have charges of positive 1 and negative 1. Magnesium and sulfur have charges of positive 2 and negative 2. Notice that the larger charges equate to higher melting points. So charge is located in the numerator of the lattice energy equation. Thus, there's a direct relationship between charge and lattice energy. Higher charges, higher melting points and boiling points. So, summarizing what we learned about charge and size in terms of melting points. So the first question that I would ask is, how does the size of an ion affect the melting point or the boiling point of an ionic compound? And we just saw in our previous examples that the size, as the size of the ion increases, that means they get bigger. The lattice energy, because it's in the denominator, the lattice energy actually decreases, meaning that melting points and boiling points decrease. Bigger ions, weaker force of attraction. How does the charge impact the melting and boiling point? Well, we saw in the previous slide that as the charge of an ion increases, that bond gets stronger. Melting point and boiling point are also going to increase. So, one of the last things that we're going to do today is we're going to learn about how to make Lewis structures for ionic compounds. We saw some of this Lewis structure idea in our previous chapter, but now we're really going to put these two pieces together and start looking at Lewis structures for compounds instead of for individual atoms. When we are placing electrons around an atom in a Lewis structure, we go from 1 to 8 according to the diagram at the lower left. 1 being on top, 2 being on the right side, 3 being on the bottom, 4 on the left. It's not 100%. Sometimes you'll see books do it slightly different, and I'm okay with that. If you notice the example that I have, on the left side, I have sodium, which is in group 1 on the periodic table. It has 1 valence electron. Chlorine, which is in group 17, has 7 valence electrons. After the reaction takes place between sodium and chlorine, we wind up with a sodium ion with a positive 1 charge, which has lost its electron, and a chloride ion with a negative 1 charge, which has gained that electron from the sodium. What I would like you to do now is to open the assignment called Ionic Bonding Practice. We're going to go through an example or two together so you know how to complete this on your own. Okay, we are now looking at our first assignment in this folder called Ionic Bonding Practice. In order to complete this assignment, we're going to use the draw function on Google Docs in order to move our electrons around. So double click on the drawing to edit the drawing and move the electrons. In this drawing, what you're going to do is first, on the left side, move the number of electrons around the sodium and chlorine atoms to show how many valence electrons each atom has before any reaction takes place. Sodium will have a single valence electron, and chlorine will have 7. Now remember, it doesn't have to be perfect, but we're going to move these electrons around in the order that was on the previous page. So we have 7 valence electrons for chlorine. So we're going to put 7 electrons around the chlorine atom. Notice how the electrons sort of snap into place. So we wind up with a picture that looks like this. Now, on the right side, we need to represent what this ionic compound looks like after the reaction takes place. And one of those electrons is transferred from sodium over to chlorine. So first thing is we're going to put our 8 electrons all around chlorine now, and sodium will have none. And lastly, we would like to represent the fact that once sodium loses its valence electron, it takes on a positive 1 charge. So we can write positive 1 and make that a superscript, hold down Control and hit period. And for chlorine, which is now chloride, it is a negative 1 charge. So again, write negative 1, hold down Control, hit period to make that into a superscript. Once you are done, you can hit Save and Close, and your work will be saved to your paper. Now, every once in a while, you run into a glitch. So if you happen to incur a glitch as you're trying to edit the document, there are 2 things that I would like to suggest. Number 1, you can change the zoom of your document by clicking on the 3 dots in the top right corner. Sometimes when your document opens, Save and Close will be out of view. This helps bring Save and Close back into view so you can hit that and exit your drawing. If your drawing appears to not save when you go back to your main page, double-click on it again, move one electron just a tiny bit, and try saving and closing one more time. That usually fixes the problem. We will be completing 8 examples here. For each of these examples, you're going to first set up the number of valence electrons on each atom on the left side, and then on the right side, show how those valence electrons have been transferred and the resulting charges. Thank you very much for listening. If you have questions about what we talked about today with ionic bonds, please consider stopping by office hours. Thank you very much, everyone. Have a great week.